So we looked at powers of sine and cosine when at least one of them was odd. That allowed us to do a U substitution. Now I want to look at the case where neither of them are odd, so they're both even. So we have a situation like this, cosine and sine, and all I'm saying here is let's say that those powers are some multiple of 2, making them even. Now that technique we used before is not going to work. So what we need to do is, since these are both even, we can write them as even powers of sine and cosine to some power. And then we can use our other identity. Sine squared is 1/2 1 minus cosine 2x. And cosine squared is 1/2 1 plus cosine 2x. So you'd be left with something like that. And then, depending on the L and the K, there's a lot of foiling out that has to happen there, right? You've got a binomial. The halves could come outside the integral. Half to the L and half to the K could multiply and come out. And then you'd have to FOIL out all this and FOIL out all this. You'd have a big polynomial of cosine 2x to various powers. And then this problem grows really fast because all the odd powers of cosine that you end up with, you have to use our technique for odd powers. And all the even powers of cosine 2x you have to do this process on. And then that sort of keeps knocking them down a little by little. And it quickly can be a huge problem for even relatively small values of K and L. So we typically aren't going to ask you to do these just because the amount of work is so much. But it's important to know that any even powers here could be gotten to. There is an antiderivative. There's just a lot of repetition of either the odd power or the even power approach on these. So what I'd like to do is just run through real quick the simplest situation where L and K are both 1. So we're just integrating sine squared times cosine squared. So let's do that. So first step, introduce your identity. For both of those. The halves can come out. You have a half times a half, which is a 4th. And when you FOIL these, this is kind of nice because they're conjugates there. You just end up with 1 minus cosine squared 2x, which I'm going to write as sine squared, just to make it a little easier. We could work with the cosine squared, but this just neatens it up a little bit. And now, notice what we've done. We started with a total of 4 in our degrees, right? And now we're down to a total of 2. So we've brought it down in degree. And that's essentially what would happen over here in the general case, but many, many times this would have to happen, and there'd be bigger and bigger polynomials with lots and lots of terms. So now we just reapply the identity to sine squared. So we pick up another half, which would be an 1/8 1 minus cosine. And now, the thing about that identity is it doubles the angle. As we went from sine squared x, it became cosine 2x. So since it's already 2x, that's going to double and become 4x. And now we can integrate that. X minus 1/4 sine 4x plus our constant. So typically we won't ask you to do the higher power ones just because of the amount of work, but it's important to know that it could be done, that there are antiderivatives for any combination of sine and cosine to even powers.